Hey, so here's Peewee, our test subject for today. In this video, I'll show you how to bake a vertex animation texture using my free and open source GameTools Blender add-on. First, the mesh is parented to an armature, and that armature has a few NLA clips I can select to play different animations. Our goal is to bake a series of animations into a single vertex animation texture. First, I'm going to select the armature, go to the Animation tab, and make sure the Nonlinear Animation editor is open. If the armature doesn't have an NLA track yet, I can simply add one by selecting this action strip first, then going to Track Add. With the NLA track selected, I can now add an NLA clip. Let's start with the idle clip. Then I'll add excited, sad, and trot, why not? An important first step is to remove duplicated frames for looping animations. For example, I know that the idle and trot animations have identical first and last frames, so I don't want to bake both. To fix this, I'll select those clips and decrease their end frame by 1. Next, selecting a clip and pressing G lets me slide it next to the previous one. It's extremely important to leave a 1 frame gap between each clip. Let's repeat that for the other clips. Finally, let's delete any empty action lines like so. Next, select the mesh and look for the VAT Baker panel in the GameTools sidebar. Here I do want to bake an animation rather than a mesh sequence. Under the Frames panel, I'll let the tool automatically determine the frame range from the NLA track. Set the step to 1 because I want to bake every frame, not just every nth frame. Padding is important in this case. The combined animation doesn't make sense as a single sequence. It's meant to be used with a state machine of some kind, right? Where a specific clip plays depending on the context. For example, play the run animation if the character is moving, otherwise idle. Now, if we loop the run animation using pixel interpolation for frame blending, the last frame will interpolate with the next frame in the texture, which might be from a completely different clip. To avoid that, we can add suffix padding, which duplicates the first frame of each clip after its last, and prefix padding, which duplicates the last frame before the first. I recommend adding both so that you can safely loop and reverse clips. Under the Mesh panel, set a name for the baked mesh. Make sure to check the export path. The Blender file must be saved for this option to be available. The export path is relative to the blend file. The rest of the settings should be good for exporting to Unreal Engine. Now, let's take a quick look at the texture panel. Keep the vertex count of your object or objects in mind. If the mesh has more vertices than the texture's maximum width, the data will need to be spread across multiple rows in the textures, and there are different layout methods for this. The continuous layout is experimental, avoid it unless you know exactly what you're doing. You can find more details in the wiki. Stack is usually the best option. Rows can be stored either directly next to each other or offset by the animation length. Both methods have their pros and cons, but I generally recommend offset because it supports pixel interpolation. In my case, the mesh has just under 4000 vertices, so I don't need to worry. Each row in the texture will have enough text cells to store data for all vertices for a single frame. Now I'll enable generation of the offset texture and the normal texture as well. The normals will be remapped into the 0 to 1 range so they can be stored in an 8-bit texture, keeping memory usage low. The precision is good enough for normals. Same can be done with the offset texture, but the precision loss quickly starts to show, so use this with caution. Set the output path if needed, or leave it blank to save the files next to your blend file. Then we are ready. Press bake. The process can take some time, especially with dense meshes. Once it's done, a new mesh should hint at the animation bounds. The baked mesh will also be generated. Now, at this point, I always check the UV map to make sure everything was created correctly. I want to see that each vertex is centered on its own text cell, like this. Looks good. This also allows me to double check the packing method. Here I do have one single row of data per frame. Thus, as expected, the texture width matches the number of vertices since we didn't exceed the maximum width, so that's good. Now the texture height might not match the raw animation length, and that's expected because of the added padding. We can however double check the total number of frames. Each clip gets 2 extra frames for padding, one as a suffix and one as a prefix. So 119 frames plus 2 extra per clips, 4 clips, that's 8 additional frames, and that gives us a total of 127 frames indeed. We can also review some information in the report panel. Here are the textures, offset and normal. Keep in mind the normal map was remapped from -1 to 1 to 0 to 1, so you'll need to apply a bias and scale to decode it correctly. The mesh panel provides important data like the index of the UV map to use to sample the vertex animation textures. It also shows the offset that must be added to the mesh bounds to account for vertex displacement. The bounds in the rest pose don't cover the full motion range, so this correction is necessary in your game engine to avoid occlusion issues and so forth. Finally, under animations, you'll find the start and end frames for each clip. Now these no longer match the original frames in Blender due to the added padding. So use these values in your state machine or animation system. There are also more details in the frames and units panel, sampling mode, padding and more. At this point we are done. All that's left is to import the mesh and textures into Unreal Engine and build the vertex shader. First I'm going to import the static mesh. I'll disable pretty much everything here, make sure the meshes are combined, just the basic settings I use all the time. In the static mesh asset, let's make sure distance fields are disabled. Nanite should probably be disabled as well, since it doesn't work well with vertex animation textures and tends to mess up UVs. Speaking of UVs, 32-bit UV precision is required most of the time. This depends on the texture resolution though. The higher the resolution, the more precise the UVs need to be in order to stay accurately centered on each text cell. I won't go into too much detail here, it's all thoroughly explained in the wiki, linked in the video description below. Anyway, last step, offsetting the bounds. Let's double check the values reported in Blender, or in the XML file. Same info, just in a different format. This offset value in Unreal Engine is absolute, so the mean values likely need to be negated. In doubt, enable the bounds debug view to ensure the values you're entering do what you think they do. Cool. Now let's import the textures. Set the compression settings for the normal texture to RGBA 8. And for the offset texture, use HDR 16-bit uncompressed. Also, depending on your use case, you might need to set the filter to nearest. Once again, refer to the wiki for more details. In our case, the default filter setting will be fine. Alright, let's create a material. Drag in both textures and convert them to texture objects. Create a material function called node. And if you've downloaded the Content Examples project, which includes a plugin containing all the base functions I use in these examples and can be easily copied into your project, you should find a function called mf_vat_getFrame. Copy-paste the node and search for the material function mf_vat_stack_pose_remap. And wire everything up like this. By default, the material function uses the texture coordinates at index 1 to sample the vertex animation textures, and this should work for most use cases, but if you're unsure, use the index specified in the bake report. Also, it's a good idea to ensure that this UV map isn't overridden by Unreal Engine's light map generation system. Now, the offset data is in local space, so it almost always needs to be transformed into world space before plugging it into the world position offset. The normal is also in local space, so it needs to be transformed to world space if you're using a world space material, or to tangent space otherwise. But before that, it needs to pass through a vertex interpolator for technical reasons. Again, this is all thoroughly explained in the wiki. Last step, let's play the run animation, I suppose. So what was it? Start frame is 110, number of frames is 16. And voila, it just works.